Hi everyone, welcome back to week 2 of biostatistics. And this week we are going to talk about hypothesis testing. And as a broader theme for this week, we're also looking now at bivariate analysis. Last week we looked a little bit at the difference between two proportions or the difference between two means and looked at confidence intervals around those. Now we're going to perform formal statistical tests to determine whether there are differences across groups on some outcome of interest, whether there's differences across categories, two categorical variables. And so this week we are now kind of in the table 2 portion of our manuscript preparation, looking at some associations among variables. Often in biostatistics, we're interested in looking at multiple variables simultaneously. So this is kind of the second step that we would take in performing analyses. Now, if we had a pure randomized experimental design, we might be able to get away with a simple test based on which group a person was assigned to and looking at an outcome without much statistical adjustment. However, in many other settings where we're doing observational studies, we'll want to consider multiple variables. And we'll address that in week 3. So this week we're focusing on bivariate analysis and what we call hypothesis testing, which is the second part of inferential statistics, the first part being confidence intervals, which we covered last week. So just like when I asked you to take that leap of faith into parametric statistics where we estimate some parameter based on our sample mean. In this case, we're going to compare two group means and say, okay, in our data, they appear to be of a certain value. Is the difference that we observe in this data likely to be real? Okay, so if we were to calculate two group means and we found them to be different, how likely is it that those two means are actually different? Or were they just by chance different from the way in which we sampled the study? Just by laws of probability, we may end up with two groups that look a little bit different. So when we're making comparisons, we want to make sure that what we observe is likely to be real, if that's what we're interested in terms of our hypothesis. Or if they're similar, that could be interesting too. But the only way to know that is to set up a formal statistical test. So we're going to learn to define the null and the research hypothesis. In this session, we're going to focus on t-tests and ANOVA, and the level of significance, and also a decision rule for rejecting the null hypothesis. Distinguish between type 1 and type 2 errors and their implications for research and for science, and to estimate and interpret p-values. And if you've not had a statistical course before, some of these terms may be new. I hope that you'll use the key terms for this week to review some of these concepts, but I also strongly encourage you to read chapter 7 in your book, which goes into hypothesis testing and some of the logic behind it. It's a hard thing to describe in lecture format, but it's a little easier to read it and have it kind of sink in what we're actually doing when we set up a hypothesis test. And we're going to move through this material fairly quickly so that we can continue our journey towards where we really want to get, which is multivariate analysis. But for now, we're going to do some more groundwork as we progress in our understanding of biostatistical type concepts. We're also going to discuss the relationship between confidence interval estimates and p-values in drawing inferences. There's actually a movement within public health, epidemiology, and biostatistics to simply report confidence intervals with the idea that they can provide as much information as a p-value. And there are some pretty strong reasons that that might be the case. The convention is now to present both a confidence interval and a p-value. And some of that is based on just pure convention, but presenting both pieces of information allows users to have the most information to make a decision for themselves how much they believe your results. Okay, we're also going to appropriately interpret the results of a t-test and an ANOVA, which an ANOVA sounds like some sort of celestial object, but ANOVA just stands for analysis of variance. And we use analysis of variance whenever we have 3 or more categories on a categorical variable, and we're interested in looking at differences in means across those 3 or more categories. A t-test is going to be when we have 2 groups, but we want to know if those 2 groups have different means. So what we actually are interested in is differences in, say, treatment effects. So if one drug can lower cholesterol more than another drug, that might be considered superior to what is currently on the market. So as we move forward here in hypothesis testing, I want to distinguish statistical hypothesis testing from what we do as scientists and researchers when we develop a hypothesis. And this is where hypothesis testing in a statistical sense may seem a little bit backwards, and we'll see why that's the case. But we start off with a research hypothesis, which is basically that we expect there to be some kind of difference between groups. Often in epidemiology, especially, we're looking at things that might be risk factors, or we might be looking for treatment effects of a drug. So we start off with a research hypothesis about some unknown parameter. That parameter could be the difference between 2 group means. As we move into later this week, we're going to talk about difference between 2 proportions. And so we use sample data and analyze that to determine whether the evidence supports our research hypothesis, or we can't say that we have enough evidence to support our research hypothesis. So the null hypothesis, which I referenced a couple times, is that there is no difference or no change or no association between 2 variables. Okay? The exact opposite of what we're interested in usually in a research context. And again, it's kind of a conservative approach in the sense that we're going to say that unless we have enough evidence based on probability, that we're going to say that there is no difference. So we then set up a test to see how likely it is that the null hypothesis is true. So the research hypothesis is what we actually believe to be true. We also call that the alternative hypothesis to the null hypothesis. And that's what we're really interested in. Is there a difference? So we have to set up a decision rule for rejecting the null hypothesis. And we do this by using a probability distribution. And from that probability distribution, we're able to obtain what's called a p-value, which is really just the probability that the null hypothesis is true. So by convention, we often use a statistical significance level of p less than 0.05, or an alpha level of 0.05. And what that says is that literally the null hypothesis has about a 5% chance of being true, 0.05, 5% chance. So it's really, we state the probability of the null hypothesis being true in terms of probability, and that's what a p-value represents. And so the smaller and smaller that p-value gets, we say 0.01 or 0.001, then we say it's very, very unlikely that our null hypothesis of no difference or no association is true, and therefore we can accept the alternative hypothesis that there is a difference. Okay, the logic on that may seem quite backwards, but it prevents us from making too much out of small differences in our data, which may just be due to chance. So we're able to use probability distributions to say how likely is it that what we're observing is simply due to chance. So a p-value of less than whatever we set at alpha, which is usually 0.05, means that the null hypothesis is unlikely to be true. Again, less than 5% likely to be true. When p-values are less than 0.05, the observed difference is not likely to be due to chance. Okay, so again, when we take samples from a population, we know that we're not actually capturing everybody in our study. We have a sample from a population. And just by chance alone, who we sample in our study could be slightly different than another group. There's just going to be noise in our data or error just by nature of taking samples. And we can try to minimize that by taking very large samples, as we'll see. But there is always inherent error when we have a sample as opposed to access to information on an entire population, which we never do. So one test that we will perform, and in your book, we see z-tests along with t-tests. You're probably more familiar with the t-test if you've taken previous stats courses, but they're really kind of a similar test in that we have two groups, a categorical variable. It could be treatment yes versus no treatment. It could be something like sex, male versus female, but the important part is we're comparing two groups on some continuous outcome or interval measure where we're computing means on those two groups. And so let's, as an example, say our outcome is blood pressure. We saw this when we were calculating means, okay? Well, now we're gonna say with two different groups, are they different, okay? So in this case, we're gonna have a treatment versus a placebo being a sugar pill or not an actual treatment. We could also do something like men versus women. Now, normally we use t-tests to look for associations among a categorical variable with two values, but we should be using it for more randomized type studies. That was his original intent, to take two independent samples and see if they're different. But if we are interested in comparison, a t-test is a pretty useful tool as long as we have reasonably balanced size of groups in our study. As we get into z-tests, which are based on larger samples, we can relax some of those assumptions that we have for a t-test. But a t-test or a z-test, basically we're taking a continuous outcome and then two independent samples. And by independent, we mean that they're different people. They're not the same subjects, or the preferred word is participants, but you'll often see subjects use the term. So when we say a sample of men and a sample of women, we're talking about different individuals. Okay, there are examples where we can do what are called dependent tests, and that's where it's the same individuals, and we'll talk briefly about that. So the null hypothesis is that the mean of one group, signified here, is equal to the mean of the second group. Another way of saying that is that subtracting one mean for another is going to be 0. Those two are basically saying exactly the same thing. The alternative hypothesis is that either group 1 is higher mean than group 2, or group 1 is less than group 2, but overall that group 1 is not the same as group 2. And we have some leeway in setting up a test to say we're really only interested in one direction. It's fairly rare to set up that kind of test, but it does happen, particularly in clinical trials where we might expect or only be interested in an improvement over the previous drug versus maybe being less beneficial. But we'll save that piece for later. So the null hypothesis for an independent samples t-test is going to be that the means between two groups are the same, or 0, or null. Okay, so there are two different statistics that we can calculate. And again, a statistic is something that we calculate based on our sample for performing this type of test. And I provided here the formula for a t-test and also a formula for a z-test, which is based on a larger sample. You can see that they're identical. The difference is that the probability distributions for those tests are slightly different. As we get to larger and larger samples, the sampling distribution starts to take a shape that doesn't really change that much as you go from get to larger and larger sample sizes. However, for smaller samples, the shape of that probability distribution, the likelihood that we could be making an error changes quite a bit, especially in the first few sample size increases from 10 to 20 to 30, we get a lot of bang for our buck in terms of the ability to make inferences as we approach, say, a sample size of 100 or 200. It's when we start to get larger and larger sample sizes that the trade-off in terms of sample size isn't quite as great. So the t-distribution has a slightly different distribution, and it's actually a family of probability distributions, which you can look up in a table in your book, table 2 in the appendix, and that you can look up a critical value for a specific alpha and determine whether something's statistically significant. In this course, we're going to mostly use SAS and our calculators to determine whether something's statistically significant. But do just know that there is a different underlying probability distribution as we go from smaller samples with a t-test to larger samples with a z-test. But they're basically doing the same thing and have similar assumptions about the underlying populations. So we're going to look at a clinical trial to assess the effectiveness of a new drug in lowering cholesterol. Okay, so we're going to randomize this treatment to one group, and the other group is going to receive placebo or, say, not receiving the treatment. So after 6 weeks, we're going to measure their cholesterols, placebo versus the intervention group. And is there evidence of a statistically significant reduction in cholesterol for patients on the new drug? So in the old days, when we did clinical trials, we could actually get away with just performing a simple t-test between two groups in an experimental design, and that would be it. That would be as fancy as our statistics need to be. And for some trials, that is all that is needed. But usually, as we'll talk later, we do need to do some additional adjustment for other factors. Usually this is when randomization isn't perfect, or we have sampled from different clinics and we have to account for variance across the different clinics, and that's pretty complicated. But in a traditional setting, an experimental setting, let's say we're doing a rodent study and we're giving one set of rodents one treatment and one set of rodents another treatment, one sample, we'll often use a t-test. Often psychology tests are also based on smaller samples, 30, 40 people in each group, in which case you'd use a t-test. Okay, so in this case, we've got a really small sample size of 15 versus 15. Apparently the budget for this project is not great. But we're going to look at the new drug versus the placebo, sample size of 15 in each group, and we observe, this is at 6 weeks, that the mean cholesterol in one group was 195.9, and the placebo group was 227.4. And you might be, eureka, I'm going to make $1 million, or these days, $1 billion on my new drug. Well, the question is that difference real? And if it is real, how wide of a difference can we expect there to be? Knowing that there's a certain amount of error simply due to sampling error in the means that we get for two groups. Okay, it might not be real. So we use a t-test to say, okay, how likely is it that we would find two means as different as they are here just by chance alone, just by pure random chance of how we selected the sample? Okay, so 195.9 cholesterol and then 227 feels like a pretty big difference in terms of cholesterol if you think about the clinical meaning of that. But however, that right now we're just purely interested in the statistical difference, and then we can save interpretation for later. So again, this is also based on 15 people, so it's not a very large sample. Okay, so we're going to test whether or not our intervention is actually lowering cholesterol. And we're going to do a formal statistical test. The null hypothesis would be that the two means are equal in terms of cholesterol. Our research hypothesis is that the group 1 is actually going to have lower cholesterol than group 2. Although we would probably set this test up as a two-tailed test where we'll allow it to go in either direction. It is conceivable that we implement a new drug and it actually has the opposite of effect opposite effect of what we thought it would. So we often will set up two-sided tests. It really depends on the possibility or the likelihood that you would expect to find an actual diminishment of effect relative to placebo. So we're going to set the alpha at 0.05. The p-value, anything p less than 0.05 will be considered statistically significant. We will reject the null hypothesis. And that 0.05 alpha is sort of a convention that we use for the level of probability that we will reject the null hypothesis. We'll say that the null hypothesis is unlikely to be true. And this is a pretty arbitrary rule, but it's what science uses for a lot of medical research. And it does depend. As we get larger and larger sample sizes, we may actually want to be more conservative and use a p-value of like 0.01. So I don't want to say it's universally true, but 0.05, you'll see in the medical literature, is often the criteria for statistical significance. Okay, so we're going to set up a test statistic, which is again based on a sample, and we calculate the actual means in this group, the sample means in this group. And in this case, we're going to use what's called the pooled variance. And basically, we have the variance from one group and the variance of another group, and we're going to pool those. And we can do this whenever the variances are similar or the standard deviations are similar. If they're very different, then we actually need to do a correction for that, but I'm not going to go into that right now. So we're going to first calculate our t-value, but we also need to find a value for t for which we can reject the null hypothesis based on our t-statistic. And as I mentioned, the t distribution changes depending on the sample size. So the way that we work with these t values is to look them up in a table, similar to what we did with the z statistic. But in this case, we're going to first say, well, how big is our sample size? Because that's going to determine the shape of that t distribution. So instead of doing pure sample size, we do what's called degrees of freedom. So here we have df equals the sample size of one group plus the sample size of another group, minus 2, which is the number of parameters that we're interested in. And so our value here is 28. So we can look this up in table 2 in our textbook, and it'll give us a value. You just have to take my word for it, that the value is 1.701. You can look it up in a table if you'd like, but the critical value is 1.701. That means that anything less than that, in the case of our null hypothesis, that the means are not different. In this case, our null hypothesis is there's no difference in mean. We're setting up this alternative hypothesis that the mean of the treatment group is lower than the mean of the placebo. So a t-value of less than negative 1.7, we're going to say we reject the null hypothesis. And we can use a statistical software package to calculate an actual p-value for this test. But we could just look this up in a table as well. So to calculate that pooled variance, we're simply going to take the standard deviation of one group and the standard deviation of another group, square those to get the pooled variance, and then take the sample size of each group and subtract 2 again, and then take the square root of that. So we basically get a pooled standard deviation for our 2 samples, okay? And then our t-statistic then is, the calculated value is negative 2.9, which is in fact lower than our critical value of negative 1.7. Now we could say it has an absolute value greater than 1.7. So we have statistically significant evidence at an alpha of 0.05 that the mean cholesterol level is lower in patients on treatment as compared to placebo. And because we set our alpha, and that's what we looked up for our critical value, we can say then the p is less than 0.05. Again, we can use a statistical software package that will allow us to just simply calculate the exact p-value for this test. which 99% of the time is what we will actually do in real statistics. But know that the important thing with the t distribution is to know that it really does depend on the sample size, whether the t statistic is going to be statistically significant or not when we calculate that value. But it really doesn't have intuitive meaning, right? Negative 2.9. So we look that up in the table 2 in your appendix in your book, or we let software calculate our p-value. So in this case, we can reject the null hypothesis and say that there is a difference between our two groups. ANOVA is used when we have 3 groups. Okay, this example, we only had 2 groups. And this test is actually quite a bit different in terms of the mathematics behind it. However, the underlying principles and the concept of ANOVA is very similar to a t-test. First of all, we have a continuous outcome, and we're interested in differences across multiple groups. We could even have 3 different treatment groups. We could have treatment A, treatment B versus placebo, or we might have something like different race ethnicities that we want to compare, or anything with 3 or more categories that we would like to explore differences. And in this case, the null hypothesis is slightly different, which is that the group mean of one group is the same as the group 2, as the same as group 3. We could also say that group 1 minus group 2 equals 0, group 2 minus group 3 equals 0, group 3 minus group 1 equals 0. Basically, there's not a difference among the means, is our null hypothesis. The alternative hypothesis for ANOVA is that the means are not all equal. Okay, so we're not going to say which pair of means are different. We're not going to say group 1 versus group 2 is different, or group 1 versus group 3. We're going to say, are there any differences across these means? And so that's important to keep in mind when you're interpreting results from an ANOVA, that it's really, when you get your p-value, we're going to only be able to conclude that there are some differences. Then we can do what's called a post hoc test to see which specific means are different. But usually we're just interested to see if there's an overall difference across the means. Okay? And this uses a different test statistic, a different distribution, and we use what's called the F statistic. And likewise, in your textbook in table 4, you can look up the distribution for the F distribution. And again, we're going to let the computer calculate this for us in real practice, but this is the actual test statistic that we would use for ANOVA. And again, the big difference here is that we have 3 groups instead of 2 groups. Okay? So those are the most common situations where we're interested in comparing independent groups and looking for differences. We may want to, however, do a different type of study design where we have the same participants at 2 different time points. Okay, so we have pre-test scores and post-test scores. Well, that actually violates one of the assumptions of a t-test, which is the independent sample t-test, where there's no dependence in those groups. So if we do a paired t-test, we actually have to use a slightly different test statistic, different we're going to have a different value for that test statistic. However, conceptually, it's very similar, and we can use statistical software to calculate a paired t-test. But it is important that we not use an independent sample t-test when we know that there's some sort of clustering within our data, that is, that there's some dependency, in this case, the same person at 2 time points. Likewise, if we're looking across time over the same subject, we might use what's called a repeated measures ANOVA. So instead of having 3 different groups, we have 3 different points in time, time 1, time 2, time 3, and we would use what's called a repeated measures ANOVA. Some of this is getting a little bit outdated now. We have what are called general linear models that are often used to deal with these kinds of situations, but historically we've used repeated measures ANOVA and paired t-tests for any kind of situation where we have paired observations on the same individuals. Likewise, there's other tests that we can do on continuous variables with different groups. One's called MANOVA, where we have multiple continuous outcomes and multiple groups. This is rarely used, but this would be where we have, let's say we not only wanted to look at cholesterol levels, but we wanted to look at something like resting heart rate at the same time, or some other continuous measure. Well, because those observations on the subjects are also dependent on each other, we would use MANOVA. So if we wanted to look at multiple continuous measures at the same time, and then we had multiple groups. ANCOVA is analysis of covariance, and we will get into this when we get into regression techniques. But basically, it's adding an independent variable or another variable as an adjustment. And in practice, we rarely use ANCOVA. We often just use some form of linear model. So I'm not going to spend a lot of time going over a methodology that we don't often use. So in general, hypothesis testing, researchers cannot prove that the research hypothesis is correct or incorrect. Instead, what we do is we use the laws of probability to make decisions about whether the null hypothesis is probably incorrect at specified levels of probability, something we call a p-value. Okay, so when we say that something is statistically significant, p less than 0.05, what we're saying is that the null hypothesis is very unlikely to be true, that there is sufficient evidence to suggest that the null hypothesis of no difference is unlikely to be true. So rejection of the null hypothesis lends support to the alternative hypothesis, which is what we're actually interested in finding. In this case, we were looking at treatment, and we wouldn't do an experiment on treatment if we didn't think that there was going to be a difference, right? But the way we set it up is the null hypothesis is there's no difference. How likely is that null hypothesis to be true? And if it's very unlikely to be true, then we say that it supports our alternative hypothesis. Again, it's similar to the innocent until proven guilty, if you want to think of it that way. It feels very backwards, but once you get a kind of hang of it and really think hard about what a p-value actually represents, then it becomes a little easier to grasp this concept. So in this discussion of p-values, I've kind of said how it is a little bit arbitrary, that we say, okay, this is enough evidence to reject the null hypothesis. And basically what we're saying is that we know that we're going to be wrong sometimes. We're going to fail to reject the null hypothesis, or going to reject the null hypothesis. And we may do this erroneously, just because we don't have access to all information. We are making inferences from samples. And so we know when we set an alpha of 0.05 that we're going to be wrong 5% of the time. And the way that we proceed in science is that we assume that there are going to be replications done of experiments, that we would want to see additional evidence. That's why we don't say it conclusively proves that we have enough evidence. What we'd want to have is sufficient evidence across multiple studies, for example, supporting the hypothesis. So without full data from a population, researchers have to make decisions about accepting and rejecting the null hypothesis based on incomplete information. If we had access to information on everyone, we wouldn't need to do studies. We wouldn't need to create samples. So there is always some risk of error, and we allow for that in scientific research. Unfortunately, what comes with that is a certain amount of skepticism, as I talked about with confidence intervals. So we're willing to make certain errors in judgment in favor of being able to make some decisions within some bounds of uncertainty, which we often define based on an alpha value. So a correct decision would be that the null hypothesis is really true, that there is no difference, and the researcher accepts that that's true, and we call that a true negative. Basically, our p-value was, let's say, 0.25, and we say we do not reject the null hypothesis, we don't have enough evidence of a difference. And the reality is that there is no difference. And so that would be a correct inference and a correct decision based on that evidence. We could have where the null hypothesis is really false, there is a difference, and we see that and we reject the null hypothesis, and we call that a true positive result. And so that's really what we want, and we set up the task to allow ourselves to make some decisions based on our data. However, there is a risk that we are making an error. And so there are two types of errors that we could make when we do these hypothesis tests. Type 1 error is where the null hypothesis is really true in the population, but the researcher rejects it, meaning we got a p-value of 0.049, and we said it was statistically significant. But the truth is that if we were to had access to the full sample, the full population, there would be no difference. And we said that there was. And so this would be a false positive or a type 1 error. And the way around this is to be a little more conservative. We could set an alpha value of 0.01, and that would help us to minimize this risk. And you'll see some studies where they'll use an alpha of 0.01 or even 0.001, depending on the sample size. So there's nothing magical about the 0.05, but we set it up to minimize type 1 error, which would be to have a false positive result and reject the null hypothesis when in fact the null hypothesis was true. Type 2 error, something we also call beta error, is that the null hypothesis is really false. Okay, in the real population there is a difference, but yet we set up this research study and failed to detect that difference. Usually we talk about this being a power issue. We don't have enough power to detect a difference, even though it actually exists. And so what would happen in that case is that we may make a decision and say, hey, this doesn't seem to have any effect, when in fact it really would. We don't know this to be true. We can't say for definitive, there is some chance that we would falsely fail to reject the null hypothesis. Okay, and as we'll see, there are ways to control error, to control type 1 error. It's set to the level of significance. Okay, so I said 0.05, we can change it to 0.01, we can change it to 0.001, but again, we're still going to have some degree of risk of making a type 1 error. That is to say that there is no difference, and we said that there was a difference. Like I said, most cases we're going to use an alpha of 0.05, which is a 5% risk of making a type 1 error, which is very similar to when we were talking about the confidence intervals earlier, where we said the 95% confidence interval likely contains the true population parameter. We could be wrong 5% of the time, but we're willing to accept that risk, and this is where we think it falls. Very similar logic, and so that's why I said earlier that confidence intervals can often share as much information as the p-value. Okay, so for small p-values, less than 0.05, we reject the null hypothesis. Your data don't support the null hypothesis, and your evidence is beyond a reasonable doubt, we say, or it meets our criteria for doubt. For large p-values greater than 0.05, okay, so 0.1, 0.2, 0.3, you can't reject the null hypothesis. If a p-value of 0.30 would mean that the null hypothesis has a 30% chance of being correct, and we don't want to take that kind of chance. So you don't have enough evidence against it. You fail to reject the null hypothesis, and you say that there is no difference. If your p-value is close to 0.05, no fudging here, your results are considered marginal. And you will see people say that things are marginally statistically significant, let's say at 0.06. I don't recommend doing that. However, if you're just looking at your data in preparation for analysis and you're trying to determine the associations among variables, we might do some use of looking at marginally significant relationships with the idea that under adjustment or in a multivariate model that it may actually be important. We don't want to lose that information. And so there are times where we will say that p slightly greater than 0.05 is okay to include that in our study or continue to look at it, but we shouldn't say that something is statistically significant unless it meets our predefined criteria based on the p-value. To minimize type 2 errors, which is when we fail to reject the null hypothesis when in fact the null hypothesis is false, we often call this a beta error or a power error. And in chapter 8, it goes a lot into power and sample size calculations. As a biostatistician, I get asked to do this all the time. How big of a sample do I need to detect a difference of a certain size? It's my least favorite thing to do, but thankfully there are calculators out there that allow you to determine in advance what the likelihood is of making a type 2 error. I'm not going to go a lot into calculating sample size and power in this class, but the power of a statistical test to correctly reject a false null is 1 minus beta. So we set a beta value that we're, again, willingness to make a type 2 error. But we really can't do much to control that error other than increasing the sample size. And so usually what we do when we calculate sample size is a range, and we try to go towards the higher end with the idea that we don't want to set up a whole study, find nothing, and make a type 2 error. So we will try to increase our sample size. Usually that's just group sizes in an experimental design, or just having a larger data pool for multiple years or something like that if it's an observational study. So that's how we minimize that kind of risk. So next time we're going to talk about chi-square tests, which is when we have a categorical variable as our outcome, and we want to know if there are differences by another categorical outcome. Okay, so the t-test and ANOVA that we looked at today and hypothesis testing there are based on having categorical variables as our independent variables and having a dependent variable, which is continuous or interval. Next, we're going to look at chi-square tests where we have 2 categorical variables. And chi-square tests are really powerful in epidemiology and biostatistics because often we are using things like exposed versus not exposed, disease versus non-disease. Often in medicine and public health, we think in terms of diagnoses. And so chi-square tests are super important as a background for future work when we get into logistic regression. So that's what we'll hit next time. Hopefully this made sense. Through some practice, we'll do some demonstrations of performing t-tests in the live session, and hopefully it'll stick after some practice. All right, see you next time. Have a great day. Bye.